The greatest structures on our planet show that human ambition has never known limits. Stone blocks weighing hundreds of tons were lifted into place. Massive hydroelectric dams hold back entire rivers, while towers rise to heights once thought impossible. Some structures were built with nothing more than stone and human labor. Others required steel, concrete, and enormous modern machines. They were built in different eras, but all demanded engineering, human effort, and years of work to complete. Their scale and the way they were built have made these structures remarkable milestones in the history of human construction. Join us as we explore the greatest structures across our planet, from ancient wonders to modern megastructures that continue to redefine the limits of what humans can build. Before the buildings appeared, Palm Jumeirah was only open water. Engineers had to create about 1,384 acres of new land, reaching nearly 3 miles into the Arabian Gulf. About 3.3 billion cubic feet of sand was dredged from the seabed and positioned by GPS, while about 7 million tons of rock formed the huge breakwater surrounding the island. But dumping sand into the sea was not enough. The new ground had to be compacted by vibration to make it denser and reduce the risk of movement under the weight of the structures above. On the outside, the crescent-shaped breakwater, about 7 miles long, was designed to absorb wave energy and protect the inner part of the island. From that artificial land, an urban area took shape with homes, hotels, marinas, and about 25,000 residents, turning the sea reclamation project into a real part of Dubai. Seen from above, the giant palm shape in the sea shows the scale of this achievement. People did not just build a structure on the ground. First, they had to create the very ground on which to build it. At more than 2,300 feet high on the summit of Corcovado, Christ the Redeemer turns a mountaintop above Rio de Janeiro into the foundation for a giant monument. The statue itself is 98 feet tall, reaches 125 feet, including its pedestal, and weighs more than 1,100 tons. Inside, the reinforced concrete structure forms a frame strong enough to hold the giant human figure with 2 arms stretched wide over the mountainside. The surface is covered with thousands of small pieces of soapstone, a material chosen for its ability to resist weather erosion. Completed in 1931, the structure was later voted one of the new 7 wonders of the world. Christ the Redeemer combines terrain, structure and sculpture to turn the entire summit of Corcovado into a monument visible from many areas of Rio. For nearly 3,800 years, the Great Pyramid of Giza held the title of the tallest man-made structure in the world, even though it was built before modern machines existed. Built for Pharaoh Khufu about 4,500 years ago, the structure originally stood about 481 feet tall and was made of about 2,300,000 stone blocks. The base of the pyramid is almost perfectly level, and its four sides are aligned very closely with the main compass directions. The granite blocks used in the king's chamber also had to be transported from Aswan, about 500 miles south of Giza. Millions of heavy stone blocks had to be quarried, moved and lifted high using methods that researchers are still working to understand. After more than 4 millennia, it is still the only surviving wonder of the 7 wonders of the ancient world, proving the extraordinary scale, precision, and organizing power of ancient Egypt. A machine weighing about 1,800 tons can turn and lift boats using only about 1.5 kilowatt hours of electricity for each operating cycle. That is the Falkirk Wheel, the only rotating boat lift in the world, about 115 feet high, connecting the Forth and Clyde Canal system with the Union Canal. In the past, boats had to pass through 11 locks and 44 gates, a journey that could take almost a whole day. Two huge water-filled caissons always balance each other according to Archimedes' principle. So when one caisson goes up, the other goes down at the same time. The Falkirk Wheel shows greatness through a rare engineering paradox, moving boats and hundreds of tons of water with one giant motion while using very little energy. Instead of opening a road through the mountain, engineers in Zhangjiajie built a vertical elevator system right on the cliff face. The Bailong Elevator is 1,070 feet tall and is recognized by Guinness as the world's tallest outdoor elevator. About 561 feet of the upper part of the structure is attached directly to the quartzite cliff, while the rest lies deep inside the mountain. 3 double-deck elevators can carry dozens of passengers on each trip from the foot of the mountain to the heights in only about 2 minutes. Thanks to this vertical transport route, the journey to the summit area, which once required long mountain roads, has been shortened to just a few minutes. The Bailong Elevator has turned an almost vertical cliff into a transportation route more than 980 feet high, where engineering is attached directly to the natural terrain instead of flattening it. Burj al Arab was not built on the Dubai shoreline. First, engineers had to create an artificial island about 920 feet from the mainland. From that foundation in the sea, the building rises 1,053 feet, with a shape inspired by the sail of an Arabian dhow. To hold the entire structure on sandy ground, more than 230 concrete piles were driven about 130 feet deep into the seabed. The outer frame helps the building resist wind forces, while its curved form turns a complex structural challenge into an easily recognized architectural icon. Inside, the central space is more than 590 feet high, creating one of the largest hotel atriums ever built. Burj al Arab turned part of the sea surface into the foundation for a giant tower, making offshore construction engineering a symbol of modern Dubai. When it was completed in 1889, Eiffel Tower rose about 984 feet, lifting an iron structure to a height never seen before at that time. The tower's frame was assembled from 18,038 iron pieces, joined by about 2.5 million rivets. Each piece was calculated and made with accuracy to about 1/254th of an inch before being brought to the construction site. The 4 curved legs of the tower were designed to transfer the weight down to the foundations, while also helping the structure resist wind at great height. Although it weighs about 7,300 tons of iron, the entire tower took only 2 years, 2 months, and 5 days to complete. Eiffel Tower turned thousands of pieces of iron into a structure of unseen height, opening a new chapter for metal construction engineering on a global scale. Instead of forcing ships to sail around South America, people cut a waterway through the Isthmus of Panama, directly connecting the Atlantic Ocean with the Pacific Ocean. The canal is about 50 miles long, but the greatest challenge was to move ships across land that sits higher than sea level in the middle of the continent. The lock system solved that problem by raising ships about 85 feet to Gatun Lake, then lowering them back to sea level on the other side. Even more amazingly, this raising and lowering process uses the force of water and gravity instead of pumps, through huge channels inside the lock structures. Engineers also had to dig through about 8.5 miles of rock and limestone at Culebra Cut to open a passage through the Central American Ridge. The Panama Canal achieved what for centuries had been considered impossible, turning a strip of land that separated two oceans into one of the most important shipping routes on the planet. The Statue of Unity raises the figure of Sardar Vallabhbhai Patel to a height of about 597 feet, making it the tallest statue in the world. Unlike a regular tower, engineers had to keep a giant human figure with very slender body proportions, stable against wind and earthquakes. Inside, two vertical concrete cores support the steel frame, where about 6,500 bronze panels form the outer skin. The structure was designed to withstand winds above 112 miles per hour and earthquakes with a magnitude of up to about 6.5. The Statue of Unity turned the shape of a human being into a structure as tall as a skyscraper, where sculpture, steel, concrete, and structural engineering come together to create a global record. More than 130 years ago, three giant steel structures reached out from the two shores of the Firth of Forth to create one of the boldest cantilever bridges ever built. When it opened in 1890, the main spans of the Forth Bridge, more than 1,700 feet long, set a world record and held that position for many decades. About 53,000 tons of steel and 6.5 million rivets were used to create the huge load-bearing frame. The cantilever arms extend from towers about 360 feet high, balancing the loads before being joined to the suspended spans in the middle. More than a century later, the bridge still serves about 200 trains each day, continuing to carry both passengers and freight across the estuary. The Forth Bridge turned Victorian-era steel and rivets into a giant structure that is still working after more than a century, raising cantilever bridge engineering to a scale never seen before. What happens when a giant river is locked back by a human-made structure? The answer is the Three Gorges Dam on the Yangtze River, a concrete wall more than 7,500 feet long, able to hold and regulate a huge reservoir. Inside the system are 32 main generating units, bringing the total installed capacity to about 22.5 gigawatts. To control the power of the water, the dam body, reservoir and spillway gates must work together continuously as the river flow changes. A 5-level ship lock system also lifts vessels across a water level difference of more than 330 feet, turning the dam into part of a water transport route. Today, the Three Gorges still holds water, generates electricity, and carries ships across the Yangtze, showing the scale at which modern engineering can affect an entire river. The Gateway Arch creates a geometric paradox in St. Louis. It is 630 feet tall, and the distance between its two legs is also exactly 630 feet. Instead of needing an inner frame, the structure's double steel skin carries its own load along an inverted catenary curve, transferring the weight down into the two legs of the arch. Each leg is anchored by a foundation 60 feet deep, with about half of it set into bedrock to resist strong winds and the thrust of the entire arch. Engineers joined 142 steel sections, using nearly 900 tons of stainless steel to create the huge surface. The two halves of the arch were gradually raised from the ground and finally closed with the last steel section in 1965. From the bank of the Mississippi River, the Gateway Arch shows how a simple mathematical curve can be enlarged into a self-standing steel structure as tall as a building of more than 60 stories. Nearly 2,000 years ago, Rome built an arena almost 164 feet tall, able to hold more than 50,000 spectators in a single structure. Instead of relying on huge solid walls, the Coliseum used arches, corridors, and travertine stone pillars to spread the weight across the entire structure. Dozens of numbered entrances helped crowds move to the right seating areas, showing that the Romans solved both the architectural challenge and the flow of people on a massive scale. Hidden beneath the arena floor was also a network of corridors, trapdoors, and lifts that brought people, animals, and props up to the fighting surface. At one point, 28 lifts required 200 24 people to operate at the same time just to create appearances from underground. The Coliseum was therefore not only a giant arena, but a complete architectural machine where structure, movement and mechanics were combined on an astonishing scale in ancient Roman times. Angkor Wat covers about 400 acres and is recognized by Guinness as the largest religious monument in the world. In the early 12th century, King Suryavarman II had this complex built with a wide moat, an outer wall about 2.2 miles long, and 5 central towers rising above the entire temple area. The sandstone used for the structure was quarried near Kulen Mountain, about 22 miles from Angkor, creating a huge transportation challenge for the ancient Khmer people. Archaeological studies show that a network of canals connected the quarry area with Angkor, allowing enormous amounts of stone to be brought to the construction site by water. After that, the stone blocks had to be fitted together into towers, galleries, and vast carved surfaces with astonishing precision using 12th century techniques. More than 9 centuries later, Angkor Wat still stands as proof that the Khmer Empire once had the ability to mobilize materials, engineering, and human labor on the scale of an entire civilization. Mont Saint-Michel was built on a small rocky outcrop in the middle of the bay, where powerful tides can create a difference in water level of up to about 52 feet. From the 11th century to the 16th century, generations of builders had to raise an entire abbey upward within an extremely limited area. Instead of leveling the rock, they stacked rooms, cellars, churches, and corridors into many levels, so the terrain itself became part of the structure. The Gothic architectural mass, called La Merveille, keeps rising along the rocky slope, with tall walls and boldly layered spaces. During the 100 Years' War, the fortification system and the tidal landscape also helped Mont Saint-Michel resist attacks by the English army. After many centuries, Mont Saint-Michel still turns a rocky outcrop in the sea into an abbey, a fortress, and an entire village built vertically. More than 2 million blocks of andesite stone were fitted together without mortar, creating Borobudur, the Buddhist monument considered the largest in the world. Built in the 8th and 9th centuries, the complex turned a natural hill into huge architectural levels that gradually lead up to the central stupa. 5 square levels, and 3 circular levels are covered with about 27,100 square feet of relief carvings, while above them stand 72 stupas containing Buddha statues. In Java's heavy rain climate, the drainage system was built into the stone mass to carry water away from the levels and protect the structure. The whole monument is also organized as a giant model of the universe in Buddhism, turning the architecture into a journey from the foot of the temple to the top. More than 1,200 years later, Borobudur still shows that the ancient Javanese could turn millions of stone blocks into a man-made mountain, carrying both building skill and the ideas of a civilization. Abu Simbel holds 2 marvels more than 3,000 years apart. A temple carved straight into the rock mountain, and then that entire temple was moved by people to keep it from being submerged. Around 1264 BC, Rameses II had the great temple carved with 4 giant statues of himself guarding the front. The structure was also precisely aligned so that sunlight would reach deep into the sanctuary on 2 special days each year. When Lake Nasser was formed, more than 1,000 stone blocks, each weighing about 30 tons, were numbered, taken apart, and moved away from their original location. The 2 temples were then completely reassembled inside an artificial hill, about 210 feet higher, and set back inland about 590 feet. Abu Simbel therefore shows not only the building power of ancient Egypt, but also became one of the greatest monument rescue efforts of modern engineering. Before the Golden Gate Bridge was built, spanning this strait was once seen as extremely difficult because of strong winds, powerful tides, thick fog, and a nearby seismic zone. When it was completed in 1937, its 4,200-foot main span became the longest suspension bridge span in the world. 2 steel towers, 746 feet tall, carry the main cables across the wide sea gateway without needing a series of piers in the shipping channel. Each main cable is made from more than 27,000 steel wires, strong enough to carry the weight of the entire roadway below. The structure was completed after more than 4 years, when engineers still had to rely on hand drawings, models, and manual calculations instead of modern computers. The Golden Gate turned a windy strait with strong currents into a giant steel span, setting a new standard for 20th century suspension bridge engineering. At an elevation of nearly 8,000 feet in the Andes, the Inca turned a steep mountainside into a whole complex with about 200 stone structures. Machu Picchu was built in the 15th century in rugged terrain where making level ground and controlling water were already major engineering challenges. Hundreds of stone terraces held the soil on the mountainside, limited erosion, and became part of a wide water distribution system. The stone blocks of many structures were cut and fitted tightly together without mortar, even though the Inca had no steel, iron, or wheels for construction. The city was planned into farming, residential, and ceremonial areas, all adapted directly to the mountain ridge instead of completely flattening the land. Instead of imposing on nature, the Inca blended their structures into the terrain, creating a lasting heritage that has endured for more than 5 centuries. Tokyo Skytree rises 2,080 feet above Tokyo, making it the tallest freestanding broadcasting tower in the world. The biggest challenge was keeping a huge steel structure stable in a city that often faces earthquakes and strong winds. Engineers used a central pillar system with a central concrete core separated from the outer steel frame, so the two parts move differently during an earthquake. This mechanism can reduce vibration response by about 40%, inspired by the stability principle of traditional Japanese multi-story wooden pagodas. About 36,000 tons of steel were used to create the structure that rises high above the entire Tokyo skyline. Tokyo Skytree shows that greatness lies not only in height, but also in the ability to keep a mega-structure standing firm during earthquakes in the heart of a mega-city. At Chichen Itza, the Maya turned stone into an architectural system that combined building, astronomy, and belief on the scale of an entire city. The most striking structure is El Castillo, about 100 feet tall, with 9 stone levels rising in the middle of the ceremonial center. 4 stairways have 91 steps on each side, which, together with the top platform, make 365, leading the pyramid to be understood as a stone symbol of the Maya calendar. Nearby, the Great Ball Court is about 550 feet long and 230 feet wide, and INOH identifies it as the largest ball court in Mesoamerica. The whole city was also placed near natural cenotes, allowing residents to use groundwater in the limestone landscape of Yucatan. After many centuries, Chichen Itza still shows that the Maya Toltec people combined engineering, planning, and astronomical knowledge to create one of the most important architectural achievements of ancient America. In the dry, rocky mountains of Jordan, the Nabateans turned solid sandstone cliffs into a city, with many temples and tombs carved directly into the mountains. Giant facades such as Al-Khazneh were created from top to bottom, requiring workers to remove stone with great precision because mistakes were almost impossible to fix. But the greater achievement lay beneath the surface. Channels, tunnels, diversion dams, cisterns, and pools captured the rare rains in the desert. That system once helped Petra support an urban center of about 30,000 residents in an extremely dry environment. Thanks to its location among major trade routes, Petra became a transport hub for incense, spices, and goods, connecting Arabia with the Mediterranean. More than 2,000 years later, the remaining stone facades and water system still show how the Nabateans turned stone, mountains, and water scarcity into the foundation of an entire city. Sagrada Familia has been under construction for more than 140 years, becoming one of the most ambitious architectural projects of the modern age. Antoni Gaudí designed branching columns like tree trunks, helping transfer the weight from the roof and towers down to the foundations. He also used complex geometric forms to create curved surfaces that traditional architecture could hardly achieve. By 2026, the Jesus Christ Tower had raised the church's highest point to about 566 feet. Today, Digital models and modern construction techniques continue to be used to complete the ideas Gaudí left behind more than a century ago. Sagrada Familia becomes extraordinary because generations of engineers are still turning a design ahead of its time into a real structure in the heart of Barcelona. The Sydney Opera House began with a paradox. The shape of its roof had been drawn before people knew how to build it in real life. It took many years of testing geometry and structure before engineers found a way to turn those seemingly impossible curves into a roof system that could truly stand. The breakthrough came from a spherical solution, when all the shell roofs were designed as sections cut from the same sphere, so they could be produced through one unified system. The precast concrete segments were then joined with pre-stressed cables, creating large roofs that spanned the performance spaces below without needing rows of support columns. The surface of the building was covered with more than 1 million tiles, completing the sail-like form that became a symbol of Sydney Harbour. When it opened in 1973, the Sydney Opera House proved that an idea once almost impossible to build could still become one of the world's most famous achievements in architecture and engineering. A dome more than 425 feet high rises in the middle of Rome, built of stone and brick, creating one of the most ambitious religious spaces ever constructed. St. Peter's Basilica was begun in the early 16th century and took more than a century to complete, with several generations of architects following one another. Michelangelo redesigned the dome as a double shell structure, combining load-bearing ribs to carry the weight down to the 4 giant piers below. The interior space stretches more than 656 feet, large enough for huge sculptures and architectural works to still feel balanced inside. Building the dome, the facade, and the colonnade on this scale turned the church into a high point of Renaissance engineering and architecture. More than 4 centuries later, the Dome of St. Peter still dominates the Vatican skyline, showing how the building ambition of an entire age was turned into stone. Nearly 1,500 years ago, Hagia Sophia raised a huge dome over Constantinople with engineering that amazed the entire Byzantine world. completed in only about 5 years under Emperor Justinian, the building used thousands of workers and materials, brought in from many parts of the empire. The dome was more than 100 feet wide and about 180 feet high above the floor, creating an interior space of a scale rarely seen in the 6th century. 4 giant pendentives carried the weight of the round dome down to the supports below, allowing the dome to seem as if it were floating above the central space. After earthquakes and the collapse of the original dome, engineers rebuilt the structure higher and strengthened the building so it could continue to survive through many centuries. Today, Hagia Sophia still stands as proof that Byzantine engineering could once turn stone, brick and geometry into a space far beyond the architectural limits of its age. Before the Petronas Twin Towers could rise into the sky, engineers had to create a foundation system reaching about 394 feet below Kuala Lumpur. From that foundation, the two 88-story towers both reached a height of nearly 1,483 feet, once holding the title of the tallest buildings in the world. The structure uses high-strength concrete in the core and large columns to carry the enormous load while also resisting wind forces. Between the two towers, the sky bridge, more than 190 feet long, is placed on the 41st and 42nd floors, but is not rigidly locked to both buildings. This special design allows the bridge to move when the two towers sway independently in the wind, avoiding dangerous stress. Today, Petronas is still the tallest pair of twin towers in the world, turning concrete, steel, and a sky bridge into an engineering landmark for an entire nation. In the heart of Amritsar, the Golden Temple was built right in the sacred pool of Amrit Sarovar, making the whole shrine seem to float on the water. The structure took shape in the late 16th century, with 4 entrances symbolizing the welcome of people from every direction and every social class. The lower part uses finely carved marble, while the upper part is covered with gold-plated metal panels, creating the famous appearance seen today. The central shrine is connected to the shore by a narrow walkway, while the entire complex is organized around the pool and the spaces for worship. Right beside it, the langar system can serve about 100,000 free meals each day, turning the complex into a community-serving structure on an especially large scale. The Golden Temple is great, because its architecture not only creates a symbol of stone and gold, but also maintains a system of faith, welcome and service to people through many centuries. The Millau Viaduct was built by pushing 36,000 tons of steel out into open space until the two halves of the bridge deck met above the Tarn Valley. The bridge is about 1.5 miles long, and its highest point reaches about 1,125 feet, taller than the Eiffel Tower. Seven concrete piers had to carry the bridge deck across a wide valley, where strong winds made high-altitude construction especially difficult. 64 synchronized hydraulic devices slowly pushed the bridge deck from both sides at a speed of about 30 feet per hour. Lasers, GPS, high-performance concrete, and self-climbing formwork helped the project be completed in just 3 years. The greatness of Millau lies in turning a giant valley into a highway that seems almost suspended in the sky. In the middle of the Dubai desert, people raised the Burj Khalifa to a height of more than 2,717 feet, making it the tallest building on the planet. To lift a giant structure to that height, engineers had to solve the weight of the tower itself, the desert ground, and the stronger winds on the upper floors all at the same time. The solution was a supporting core system with 3 wings forming a Y-shaped floor plan, helping the whole structure reinforce itself and spread wind forces down to the structure below. More than 40 wind tunnel tests were carried out, while the tower's shape kept narrowing and changing with height to stop the wind from creating dangerous swaying. The result is a structure 828 meters tall that still stands firm on deep pile foundations, surpassing every other completed building in the world to this day. The greatness of the Burj Khalifa lies in the fact that people did not simply build higher, but turned a height once beyond the limits of architecture into a structure that can stand firm amid wind and desert.